So first things first, I just want to show you the schedule real quick. We're on week 8, halfway point of the semester. Test is Monday and lecture, same format as last time. We're almost there. Like chapter 16, the big difference between everything before 16 and 16 on is stats. Like the first 15 chapters is building up to confidence intervals and hypothesis tests. Once we get to that, that's really how we bring everything together. And because confidence intervals and hypothesis tests are like the core of like statistics. Like how many of you guys are like some form of STEM major, right? Aren't most of you like bio or something, right? Like you'll be doing some hypothesis tests. So you'll see it in like 2 weeks or so. It's all going to start coming together. But our last bit of setup before it all comes together starts with chapter 14, which are random variables. So, a random variable, we always denote it by a capital letter, like, X, is the numerical outcome of an event. Now, an event was a term used last week. If you flip a coin, it's heads or tails. If you have a child, it's a boy or girl, there's a chance you get into a car accident when you drive. All those things are events with some probability. A random variable is a number that corresponds to a random event. That's randomly decided. It's not like on a line where you can just pick, 2, 4, 6, 8. It is completely random. Computers can generate it, or real life experiments can generate it. We're going to be talking about random variables essentially for the rest of the class. There are 2 types of random variables. There are discrete and continuous. Discrete has a finite amount of values. Like 1, 2, 3, whatever. Continuous has an infinite amount of values. There are a few in chapter 15 probability models that we were not talking about. But I just want to, even though we're not talking about 15 just yet, I just want to show you which ones are which. Discrete, you have Bernoulli. We have binomial, geometric. Continuous, we have normal. Remember, the normal model is a continuous. We have uniform. Uniform is also can be discrete. Just off to the side, well, you don't have to know these 2. You don't even have to write this down, but these 2 are also in your textbook. You do not need to know them for the test. Poisson and exponential, but they are continuous. Sorry, that's not true. Poisson is discrete. Exponential is continuous. And how we draw it, like a discrete is like a bunch of points. Continuous is like a line in terms of graphing. That's just a little classification thing. So we want to talk about the mean and the standard deviation of random variables. So the mean of a random variable X is the expected value of X. So the mean, which we call mu, is expected value of X. That is an important definition because we might use it interchangeably on like a true or false question. The formula for a discrete random variable is the sum y equals 1 to n of xi times the probability of xi. In essence, it is a weighted average. I'm sure you guys have all like tried to calculate your averages before, right? It's a weighted average with probabilities. Remember how in chapter 2 we talked about standard deviation and variance, but variance seemed kind of useless, right? Because it's just standard deviation squared. Now we're talking about variance because variance has important properties that standard deviation does not. So this is variance. Remember that this is the Greek letter mu, and that is the expected value. I just want to derive this for you. You don't need to write the rest of this down, but this is this bottom form is the general form, which I don't know if you'll need to know. Well, we didn't use it last year, but the bottom is the general form. The thing about both of these top formulas is those are only for discrete variables, but you only really need to worry about discrete random variables because the expected value for a continuous random variable would be an integral, which you don't need to know integrals for this class, so don't worry about that. So you need to know the top formula. You should know these two formulas. Okay, everyone good so far? Now, the rest of chapter 14 is basically a bunch of rules, how you can manipulate expected values and variances. So the expected value of x plus c is just some number, is expected value of x plus c. The expected value of a times x, where a is some number, it can be 0, is a times expected value of x. Which kind of makes sense, right? If you add, 5 to every number, you should raise the mean by 5. If you multiply every number by 3, you should multiply the mean by 3. You've already done this on your first test, right? And expected value of x plus minus y is expected value of x plus minus expected value of y. Expected value has a lot of really nice properties. It works well with multiplication and addition because the formula is multiplying a bunch of terms and adding them up. So a condensed way of writing this all would be like this. You don't have to write this if the first 3 are enough, but if you saw something like this bottom one is me putting the other rules together. So expected value has a lot of really nice properties. These are definitely the kind of things you want to put in your flashcard too. Now, the variance is different because we have a squared term in here. It's not going to work as nice. So the variance of x plus c, or plus minus c, is the variance of x. This should make sense because if you add or subtract a value to all your data points, all you're doing is shifting the distribution over, right? You're not changing anything about the data. You're just moving it over. Next, the variance of a times x is a squared variance of x. Again, that's because there's a squared in the variance formula. Everyone good so far? If X and Y are independent, it's very important. The variance of X plus Y is the variance of X plus the variance of Y. If they are, remember last week with the probability rules and stuff, that's part of the reason why we needed to know about independence. If they are dependent, it introduces a thing called a covariance term. You don't need to know it for this class, which means everything you'll be working with will be independent if you need to manipulate it. First question I'm gonna ask you guys, you will 100% see this on your test or final, is the variance, so if X and Y are independent, is the variance of X minus Y the variance of X minus the variance of Y? Before someone answers me, look at the rules above on the right before you just say yes or no. Yeah, Henry.
No.
Why?
It would have to be bar X and Y minus bar Y.
What do you mean and like the and sign? What do you mean by that? You are correct. It is, the answer is no. But what was your explanation again?
I won't.
All right. So here's how you can rewrite this. Variance of X plus -1 times Y. This is variance of X plus -1 squared variance of Y. So this is variance of X plus variance of Y. This is the actual answer. Because remember, this rule over here. So if now we can have our final rule. If X and Y are independent, variance of X plus minus Y equals variance of X plus variance of Y. Does everyone see what I did in this example above? Anyone want me to say it again? Yeah.
So does it just mean if it's the variances you add or subtract them, this always be division?
If they're independent.
If they're independent.
Yeah. If they are dependent, this is not fully true. But the independence is very important because a true or false question could be, is the variance of X plus Y equal to the variance of X plus variance of Y always? You say no, because only when they're independent, you know? Easy true or false question right there. Yeah. Yeah, so right here, right? X minus Y is X plus -1 times Y, right? So then we use this rule that's in red. So A here is -1. So it's variance of X plus -1 squared, which is 1 times variance of Y. So it's variance of X plus 1 times variance of Y, which is variance of X plus variance of Y. You see that? Right over here. So anytime it's a negative number, you know, if it's -2, that becomes +4, you know, because it's negative number squared. Everyone go with these rules. Okay. The rest of the content of this chapter is kind of just doing examples. I assume you guys probably didn't do any of the problems because they were posted like last night. Please do some of the problems. You know, come to my office hours, we can talk about them. You know, chapter 14, 15 are basically all the learning is just doing practice problems. So please do some problems, you know, come to my office hours, we can talk about them before the test. You know, I'll show you an example right now of something like you'll see on the test, but it's important stuff. So there's basically 2 types of problems we can do. Everyone go with these definitions so far? Okay. So if we have a table and I said, find the expected value of this discrete distribution. The first thing you want to do before doing any math is verify that all the probabilities add up to 1. Obviously, 0.2 plus 0.4 plus 0.4 is 1. If they don't add up to 1, you can't even do the problem. So, expected value of x is the sum of x times the probability of x equals x. This would be 20 times 0.2 plus 30 times 0.4 plus 40 times 0.4. It's a weighted average. I could ask you to find the variance too, but that's just a lot more work for not much more gain. Unless you guys want me to show you it. Okay. Variance of x is the sum of the x minus mu squared p of x equals x. And what this notation means is it's the probability that the random variable equals the little x is referring to 20, 30, or 40. So this would be 20 minus 32 squared times 0.2 plus 30 minus 32 squared times 0.4 plus 40 minus 32 squared times 0.4. Can I do this in my head? That's 144 times 0.2 plus 4 times 0.4 plus 64 times 0.4. So that's 28. 56. I think. At this point, you just plug it into a calculator. And that's how you calculate expected value and variance for some discrete distribution. You'll never have to do it for a continuous one because that requires integrals. Everyone go with this so far? Really, that second line is the most important line. Once you have it set up, now we know that you know how to use the formula, and then just plug into a calculator from there. Okay, I'm going to show you an example of something like you might see on the test. X is a random variable with mean 4 and standard deviation 5. What is mean and standard deviation of 3x minus 14? Well, standard deviation is 5, yeah. You will see something exactly like this on your test with different numbers. Because this is the best way to test. This will test every single one of these rules. Well, I guess not with 2 variables. So the first thing you have to know is mean is expected value. So let's just write out what we know in notation. expected value of x is 4. What is that? Is 4. Standard deviation of x is 5. That means that the variance of x is standard deviation squared is 25. Right, you have to remember that standard deviation squared equals variance. So expected value of 3x minus 14 is, well, we're going to use these top two rules on the left. It is 3 times the expected value of x minus 14. Now we just plug the numbers in. 3 times 4 minus 14, 12 minus 14, negative 2. Expected values can be negatives. That is completely fine. Standard deviation and variance have to be positive, though. Everyone see how I got that? I just applied the rule that, expected value of ax plus c is ae of x plus c. Now, you're going to be given standard deviation. We don't have any nice rules for standard deviation. So you have to do it in terms of variance and then square your final answer to bring it back to a standard deviation. So the variance of 3x minus 14 is 3 squared variance of x. That is 9 times 25. That's 225. But we want the standard deviation. So you want to take the square root of that. Square root of 225, that is 15. This and this are your answer. You show us this, that's, you know, like 10 points on your test right there. And what you'll see is basically just the same thing with different numbers. Everyone see this? Any questions on this example? Okay. I'm gonna give you guys another one. You guys are gonna do it real quick. So we have I don't know, y has mean 5, standard deviation 10. Find mean and standard deviation of 5x plus 27. Take a minute to do that and then we'll go over it. If you get this, that's a free, you know, 10 points or so on the test on Monday. I'll put the rules up. Actually, does everyone have this copy down? No, okay. You might write as a table like mean, standard deviation, 5, 10 for x, and then he might call this y and say, fill in the rest of this box. He might write it like this, with mu and sigma. Means the same thing though, because this is mean, this is standard deviation. And here are the rules. Definitely recommend, you know, do a few problems so that you can do this in like 3 minutes or so. The day of the test. All you gotta do is just come up with some numbers. Or come to Offstars and ask me to give you some numbers. And yeah, the number might not be nice in the end. Okay. I'm going to start going through this. So this is 5, expected value of x plus 27. This is 5 times 5 plus 27. That is 52. Everyone get that? Variance is 5 squared. Variance of x. That is 5 squared times 10 squared. 25 times 100, 2500. So the standard deviation, 5x plus 27 is 50. So in this table, if he gives it like this, you just put it here.
So you just come like dropped it.
And variance, yeah.
Oh.
Because again, all that is saying we're adding 27 to all our data points, which doesn't change the spread of distribution, right? We're just moving it over to the right by 27. It's the same concepts that we learned in like chapter 2 or something, just numerically. Okay. You know, if you have any trouble with this stuff, definitely do some extra examples. This is basically it for chapter 14. This is, if you know how to do this, you know how to do this, you're good. And you know, definitely read the book for all the concepts and whatever. But yeah. Chapter 15. Here's where we start getting into the fun stuff with probability models. So the first type of probability model, I might say distribution, same thing, is Bernoulli. Usually write it Bernoulli P. And what this means is it only depends on a probability P. We call it a probability of success. Now, success does not mean a good thing necessarily. As my stats teacher said as his first example, a probability of success could be number of deaths in a natural disaster. It does not need to be a good thing. It just needs to be whatever you are focusing on is success. A Bernoulli trial only has 2 outcomes. Success or failure, heads or tails, you know, boy or girl, stuff like that. Flipping coins, obviously, like the quintessential example of like a Bernoulli random variable. You flip it once, it's either heads or tails. Probability of success for heads or tails is 0.5. Bernoulli random variable has expected value P, variance of Bernoulli is 1 over P. Wait, no, it's not. Sorry, no, it's not. It's square root of P times Q. Q is 1 minus P. It's always gonna be 1 minus P. So, you know, Bernoulli's heads or tails. From here, we get the geometric, which also only depends on P. The description in words of a geometric is very important because when you get a problem, the hardest part's gonna be determining basically, is it geometric or binomial? That's gonna be the hardest part. So it is so X, the random variable, represents the number of trials until your first success. So if you say, what's the probability I have to flip a coin 5 times to get the first head? That's geometric. You have to get 4 tails and then a head. So like writing it out, that means like tail, or let me say failure, 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 success. Now remember for last week, the independent multiplication rule? So this would be Q, your probability of failure, to the 4th, P to the 1, or just P. That would be your probability, right? Do you guys see that? So the probability model or distribution is the probability, this is capital X equals lowercase x, is Q to the X minus 1 times P. In this case, it's X equals 5. Everyone good so far? The expected value is 1 over P. The variance is Q over P squared. Again, if you want the standard deviation, just square root that. So geometric, you do not need to know the number of trials. You only need to know the probability, and it's the number of failures until, well, it's the number of times you have to do something until you succeed. Each trial must be independent. Now, you kind of need to be told this information or assume it. Like every time you flip a coin, that's independent. If I had like a box with like a bunch of different colored marbles and I picked one out, I looked at, is it red or blue? And I'm looking for red, right? Every time I pick a red out, that's geometric. If I do not put the red back in, that is not geometric because they're no longer independent. If you take them out after each time, it's changing the probability. But if you put them back, that's independent. Do you guys see what I mean? If you have like 4 red marbles, 6 blue marbles, and you take, you have a probability of 0.4 to get a red. If you take one out and you leave it out, that changes the probability every time, right? Because it'd be like 3 out of 9, 2 out of 8, 1 out of 7, stuff like that. That's called a hypergeometric. You don't need to know that. But each event, each trial needs to be independent. Everyone good with these definitions? We'll try to do some examples at the end, but I just want to make sure you at least get the information. Next, we have binomial. Binomial, I feel like, is more famous. It is usually written binom NP. N is the number of trials. P is, the probability of success. Immediately, the big thing I want you guys to notice, geometric has one parameter, P. Binomial has N and P.
What word right there before the N and P?
Binomial, we just call it binom NP.
Okay.
X, our random variable, is the number of successes in N trials. It is completely different. So geometric is how many times it takes for you to succeed. Binomial is how many times you succeed in a fixed number of trials. They are very different things. They are both made up of independent Bernoulli trials, though. But we are looking for different things, so the equations are different. Before I tell you the equation, I need to teach you a little bit of combinatorics. So How many guys have seen that before? Like in lecture? Okay. This is pronounced N choose X. The notation, I remember in high school for me, they said they were phasing this out. I use this notation, like in my classes and stuff. They mean the same thing. Like on the review sheet, you'll see the bottom notation. You say N choose X. N always has to be a number bigger than or equal to X. Otherwise, it doesn't make sense. What this is numerically is N factorial over N minus X factorial, X factorial. Now, you might ask, what's a factorial? The best way to explain it is an example. 5 factorial is 5 times 4 times 3 times 2 times 1. 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. That's what a factorial is. It's that number times all the numbers before it down to 1. Now, what does this mean? Let's say we want to find 3 heads and 5 coin tosses. Actually, let's make it 4. So you can have head, 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 tail, head, head, tail, head, head, tail, head, head, tail, head, head, head. This would be 4 choose 3, which is 4 factorial over 3 factorial times 1 factorial, which is 4 times 3 times 2 times 1 over 3 times 2 times 1 times 1. Well, that's 4. What it is, N choose X is the number of combinations of X successes in N trials. Because you need to account for all the possible iterations, right? We don't know the ordering, but this N choose X accounts for that ordering. Because we don't know out of these 4 things where the tail was. But we know it's in one of 4 ways. Everyone okay with that? This little bit of combinatorics. On your calculator, if you have your calculator with you, you can do this in a calculator. If you have like the TI 30, it's like PRB. Yeah. So that means there's 4 possible ways we could arrange 3 heads and 4 coin tosses. On a calculator, if you guys want to pull out your calculators, you write it as N, and it's usually written NCR X. So you write the N in first, then you click the NCR button, and then you type in X and then enter. If you do 4 NCR 3, you'll see it's 4. Definitely familiarize yourself with this before the test. Yeah, so you type in the first number, then you find the NCR button, which I believe, is there like a thing that says like PRB, right? And then you'll see NCR, you click that, and then you write 3 and then enter. So now let me tell you what the actual equation is. It is N choose X, P to the X, Q to the N minus X. So it's the number of possible combinations of X successes in N trials times the number, the probability of success to the number of successes times not. In the above example, it'd be 4 choose 3, 0.5 to the 3, 0.5 to the 1, which is 4 times 1 over 16, which is 1/4. I was only able to do that because the numbers were easy enough. In the future, I'm just going to tell you guys to plug that into your calculators because it gets complicated. But definitely practice plugging this into your calculator so you can just do it quickly. One thing I want you guys to notice the exponents of P and Q add up to N. Up here, the exponents add up to little x. Which should make sense in the picture, right? If you have if you toss a coin 4 times, you have the probability of success to the 3rd power, probability of failure to the 1st power. That adds up to 4 trials. Yeah, I know. Yeah. So we need 3 heads in 4 trials, right? Which means the 4th thing is a tail. And then the only possible combinations are just where the tail is, right? It can either be in the 1st, 2nd, 3rd, or 4th slot. So there's 4 possible combinations. So 4 choose 3 is 4. Yeah. Sometimes this number can get really big. I did an example in office hours where the n choose x was like 80,000. That's fine, as long as your probability is a number between 0 and 1. Like it might look really big, but don't worry about it. And you can plug this all into your calculator in one line too. Okay. Other thing, the expected value of x is n times p. And the variance of x is npq. In the textbook, they give it in terms of standard deviation, but you can manipulate variances. You can't manipulate standard deviation. If you know standard deviation is square root. I want you guys to just, I'll go back to that in a second. Notice how this is p and square root pq. And this is np and npq. That's because it is the sum of independent Bernoulli trials. There are 3 conditions you need to do this. 1, you need only 2 outcomes because each event is a Bernoulli trial. 2, well, you need some probability. 3, it's called the 10% condition. Your n should be less than 10% of the population. It's just a thing, you know, in basically any scenario, it won't be a big deal unless there's like 20 people in the world have some rare disease and you choose 3 of them, that's more than 10%. But like that rule basically won't matter. So one thing we can do is we can approximate a binomial distribution with a normal model. And to do that, we need, so to approximate a binomial with a normal, we need the success failure condition. This says n times p is greater than or equal to 10, and n times q is greater than or equal to 10. We talked about the law of large numbers last week. This is kind of the law of large numbers. We need a big enough sample size so that we get like a unimodal and symmetric histogram, so it looks normal. And this would use the mean and standard deviation of the binomial distribution, which we can calculate from these equations. Just, you know, square root the variance. You know, this is an easy point or 2 on your test. And if you want to calculate, like, let's say the probability that x equals 5 in a binomial, this is roughly the same as doing the probability that x is between 4.5 and 5 in a normal. This is called continuity correction. Number of trials times probability of success, number of trials times probability of failure. Yeah. So we can approximate a binomial with a normal, but we have to find the area plus minus 0.5. Because again, the area of a single line in a normal is 0. And that's because we're going from a discrete random variable to a continuous one. You do not need to know a Poisson. You do not need to know an exponential. We will talk about the uniform briefly. Any questions before I move on? I know it's a lot of stuff. So, yeah. Use continuity correction to approximate probability x equals 5. I guess, given some scenario. I don't know. I don't know how I'd word it otherwise. I guess like if you somehow only have the expected value and the variance without the probability or the number of trials, like if you only are given that information, you can use it for the normal. That's the only thing I can really think of. The uniform. So uniform can be both continuous or discrete. Something like a dice is uniform, right? A 6-sided dice, each side has probability 1/6 of being chosen. It can either be like this. This is the discrete picture. Or it can be continuous. This height is 1 over b minus a. Let's use some numbers. If you have a uniform between 0 and 20, the area, right, the probability of the sample space has to be 1. If you have area is base times height, 1 is base times height. Oops. So 1 is 20 times h. So the height is 1 over 20. So this height is 1 over 20. If I ask you what's the probability that x is less than or equal to 5 for some, whatever the scenario is, you put a 5 down and you calculate the area. It's 5 times 1 over 20. That's 1/4. And that's really it for the uniform. The general formula is like the probability that c is less than or equal to x is less than or equal to d is d minus c over b minus a. In this case, it's 5 minus 0 over 20 minus 0, which is 1/4. Yeah. Yes. Because that's, remember the first row probability, the probability of the space is 1. So the area is always 1. Like the area under the total normal curve, the entire thing is 1. Whenever it's a continuous random variable, the entire area of the distribution is 1. Because the probability of the sample space is 1. Well, that's the content for 14-15. I don't think I can teach you all confidence intervals. Do you want me to try to teach you confidence intervals in 15 minutes, or do you want me to do examples? What do you guys say? Raise your hand if you want me to do examples. Okay, yeah, that's what I figured. Well, what were some of the examples on your homework? Again, please work through, really, you should try to work through these homework problems. Because they were chosen for a reason and they're just good practice. You know what, I'm actually gonna do number 20 because I always liked, this is chapter 15, number 20. I always liked this one. This says a computer chip manufacturer rejects 2% of chips for being faulty. First of all, this is all the information you have. Do we have a P, a probability? Yes or no? Do we have a probability? What's the probability? 2%. Do we have an N? No, we only have a P. So before even reading the question, you know this is a geometric 0.02. In this case, a chip getting rejected is the probability of success. I don't even want to read you to the question part yet. This is all the information. This is all you need to know that it's geometric. Yeah.
Oh, how did you get the next step to it being geometric from this?
Because geometric, well, binomial has two parameters, N and P. Geometric has one parameter, P. So you need the probability no matter what. The probability might be like a little implicit, like 2 out of every 100 chips gets rejected. So then you say, okay, it's 2%. Now, part A. What is the probability that the 5th chip you find is the first one that's bad? So what's the probability that the 5th trial is your first success? So the probability of failure is 0.98. We need 4 failures and 1 success. You know, you plug that into a calculator, you get an answer. Does everyone see how I got that? What is the probability that the 5th chip you test is the first bad one? Right? You know it's geometric, so that's telling you what your little x is. So B, what is the probability you find a bad one within the first 10? So this is probability that x, well, x is like between 1 and 10. This uses that complement rule that we talked about last time, which is 1 minus the probability that there's none, that all 10 are good, which means you're failing. In this case, failing is good, but you are not rejecting 10 chips. Are there any questions on that one? You have to kind of think in terms of the Bernoulli trials and what the actual question's asking. You know, the probability of finding at least one bad one in the first 10 chips is the complement of finding no bad ones. All right, that was number 20. Any questions? Yeah.
I'm just reading the question, say again, so I hear it.
Yeah. What is the probability that the 5th chip you test is the first bad one you find? Yeah. Anything else? Okay, where are some other ones? Oh, 19 is a good one. So this is about basketball players. A basketball player makes 80% of his foul shots. Assuming the shots are independent, find the probability that blah, blah, blah. So is this going to be geometric or binomial? Right. This is our probability, right? We don't have an N. Just based off this information. So this is a geometric 0.8. So part A is misses for the first time on his 5th attempt. So in this case, actually, getting your foul shot is the failure in this case. We've kind of flipped it. So this refers to making the shot, right? But now we want him to make 4 shots and miss the 5th one. Does everyone see that? So in this, we want him to make it 4 times and miss once. You guys see that? This is 0.00, sorry, 0.081. Part B is makes his first basket on his 4th shot. So now we're going back to the geometric with 0.8. We want this to be 4. So this is he misses 3 times, scores the 4th time. And I really want you guys to think in terms of the Bernoulli trials. You know, miss, 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 score. Part C. Makes his first basket on one of the first 3 shots. This is one of those at least one problems. You know, there's a lot of those. So this is 1 minus missing 3 times. Does everyone see that? This is basically all the ways you can use a geometric. Yeah. Makes his first basket on his 4th shot. Yeah, it should kind of be written like this. Yeah. I was kind of writing it like binomial. What is a one that's not geometric that he assigns? Here we go. Let's do number 29. Assume that 13% of people are lefties. If we select 5 people at random, and then the question. So, what is our probability here? Someone say it out loud. What's the probability? If we have an n, what is it? Do we have an n here or no? It's 5, right? P n. Whenever you read these questions, what I want you guys to do is literally highlight it or like underline it in the question and then, you know, label it. This is what you need to do. So we know it's a binomial 5.13. Everyone see that? Part A. the first lefty is the fifth person we choose. So actually, this is geometric. This part is geometric because the first success is trial 5. It's the same probability x equals 5 is 0.87 to the 4 times 0.13. It's always good to just write out Q too. Knowing the difference between what a geometric and binomially random variable means is very important. Part B, there are some lefties among these 5 people. Well, doesn't this mean that this is the probability that there's at least one lefty, right? Which is 1 minus the probability of no lefties. So this would be 1 minus 5 choose 0, 0.13 to the 0, anything to the 0 power is 1, times 0.87 to the 5. This is also equivalent to just saying 1 minus 0.87 to the 5. This answer is 0.502. Does everyone see that?
You said
There are 5 lefties among these 5 people. So there is at least one lefty in this group of 5. Next is the first lefty is the second or third person chosen. This is actually going to go back to a geometric again. This is the probability that x equals 2 plus the probability x equals 3. Which is 0.87, 0.13, because we have 1 failure, 1 success, and then 2 failures, 1 success. You guys see that? It's kind of going back and forth between geometric and binomial. D, what is the probability? Well, that there are exactly 3 lefties. So it's the probability of at least 3 lefties. This case, you might just want to do it directly instead of the complement rule. This is the probability that there's 3 lefties plus the probability that there's 4 lefties plus the probability that there's 5 lefties. All these are binomial. So this is 5, choose 3, 0.13 to 3. Yeah, 0.87 to the 2 plus 5, choose 4, 0.13 to the 4, 0.87 to 1 plus 5, choose 5, 0.13 to the 5, 0.87 to the 0. Yeah. Wait. I said one thing and then I wrote, sorry. This is point E. This is at least 3. Yeah. Yep. Sorry. This is at least 3 lefties. You're right. Sorry about that. I was looking at the wrong part. At least 3 lefties is this. Just part E. It's 0.0179. Part D is exactly 3 lefties, which is just gonna be this part again. Have our quiz in a minute. One more part. This is part D. This is 0.0166. So pretty small amount. One more part. There are no more than 3 lefties. So this is probability that X is less than or equal to 3, which is the probability X equals 0 plus the probability X equals 1 plus the probability X equals 2 plus the probability X equals 3. Since they are independent, we don't have to subtract off all of the X is 0 and X is 1, X is 2 and 3, all that. Because they're independent, we can just do the easier addition rule. Now, this would just be 5 choose 0, 0.13 to the 1, 0.87 to the 4, plus 5 choose 1, 0.13 to the 2, 0.87 to the 3, plus 5 choose 2, 0.13 to the 3, sorry, 2. Oh, wait, sorry, this should be, wait, sorry, that's 1 and 4. Wait, oh, I messed these all up. Sorry, 0 and 5, 1 and 4, 2 and 3. Now it should be 3 and 2. This answer is 0.9987. So you guys see like how we're applying this, right? We're just kind of changing the numbers around a little bit. And this is a really good question because it goes back and forth between geometric and binomial just by slight different word choice of the questions. Any questions on this? Okay, let's go on. Okay. Oh, there are some lefties among these 5 people. That means there is at least one lefty, right? So probably there's at least one lefty, which is the complement of no lefties. So, all right, so that concludes 1415.